This video introduces the idea of functions. To start, we want to think about equations in general, and so we'll start by thinking about equations in one variable. An equation in one variable has a solution set that is a subset of the number line. So for example, if I thought about the equation x squared equals 25, that means I'm thinking about the number line, which I've drawn here, and I imagine going across points of the number line, and at each point I ask myself, for this value, if I square x, is it the same as 25? So for example, if I were to think about particular points like -6, at this point, x squared would be 36. That's not equal to 25, so this point is not in my solution set. If I then go to -5, and I were to square that, I get 25. That is in fact the same as 25, so this point would be in my solution set. As I go across the number line and think about my points, only at -5 and at 5 do I actually have a point where x squared is equal to 25. And so my solution set consists of only 2 points. And I would write that the solution set is the set -5 and 5. We often think about this in 2 dimensions, but in reality it is a one-dimensional problem. The way we think about it in 2 dimensions is we imagine a graph where we graph the function x squared. So here's y equals x squared. And we also graph the second function, 25. So here's y equals 25. And we go identify points where they intersect. So for example, if I look at this graph, I intersect at these 2 points where the graphs cross, and I translate it back to a one-dimensional problem by going back down to the x-axis and identifying 2 points where those functions are equal. And so I get 2 points on my x-axis. I get -5, so here's -5 and 5. So although we often think about this in 2 dimensions, in reality we are actually solving a one-dimensional problem. An equation in 2 variables has a solution set that is a subset of the Cartesian plane, which means we have 2 coordinates. An example would be x squared plus y squared equals 25. Here, instead of having a one-dimensional problem, we actually have a 2-dimensional problem. We have x and y, and now our point is no longer a single point on a line, but it could be anywhere in the plane. So let me put a box around my plane so we can isolate where we're talking about. And I now consider any point in the plane. I ask myself, is this statement true or false? So for example, let's put some coordinates on here. Let's see, we would want -5 and 5. I anticipate the answers here, so I'm just going to put these in. 5 and -5. And now we can pick some points. So for example, at this point 0, 5, x equals 0, y equals 5. Let's write that to the side. X, y equals 0, 5, which means x equals 0, y equals 5. X squared is 0, y squared is 25, so x squared plus y squared is 25, and we have that point as one of our solutions. If I think about each of these other points, so for example 5, 0, that is also a solution set. 5, 0 is a solution. 0, 5 is a solution. So each of these 4 points is a solution. On the other hand, if I pick a point off to the side, so for example, here at 1 comma 4, if I tried that, 1 comma 4, 1 squared is 1, 4 squared is 16, 1 plus 16 is 17. This is not a solution. And so as I think about all the points that might be solutions, many points are not, and it turns out that this is the equation of a circle, and our equation considers only those points that make the statement true. So as I go through my plane, all of these points are false, but as soon as I touch the circle, the statement's true, false, and true. Some other points that actually are solutions, you might be interested to know that 3, 4 is a solution because 3 squared is 9, 4 squared is 16, and 9 plus 16 is 25. So there are some other points that we know. So 3, 4 would be here. This would be 3, 4. It is a solution. And 4, 3 would be a solution. So there are some points are solutions, and this gives me a sense of what it means to be an equation in two variables. In our last example, we had the circle, and as we were thinking about the equation in two variables, we imagined moving all through the plane and testing every single point in the plane to determine if it was in the solution set. Some equations allow us to solve for a variable, and that's when we get the idea of a function. A function is a relation between two variables so that knowing the value of the independent variable allows us to know with certainty the value of the dependent variable. And that means we can solve for the variable. So here's an example. 3x plus 4y equals 12, and if I thought about this as an equation in two dimensions, I have to consider the entire plane, and I would be testing all these points, and some would be true and some would be false. But if I try to solve for a variable, so for example, let's solve for y, we get 4y equals 12 minus 3x, and then divide by 4, y equals 12 minus 3x over 4. This gives me a formula so that if I know x, I know immediately the value of y that makes it true. And this allows me to create a graph that I don't need to think about all possible points in the plane. So let's see, here's x, here's y, and if I were to graph this, it's easiest if I split this out. 12 over 4 minus 3 over 4x. So this is 3 minus 3/4 x. We recognize that this is a line. Y-intercept is 3, slope is negative 3/4, and so here's an equation or a graph of my line. And I didn't have to test all the points in the plane because I know once I have x, the value of y, there's only one value that will work. And so this is an example of a function. We would write that y is a function of x. And let's call our function f, a function of x, which is 3 minus 3/4 x. Now this is a curious example because I can also solve for x. So for example, solving for x, I get 3x equals 12 minus 4y. 3x equals 12 minus 4y. I now divide by 3, and x, one way to write it is 12 minus 4y over 3. Or I could write it as 4 minus 4/3 y. Now because I've solved for x in terms of y, x is a function of y. X is a function of y, just as y is a function of x. We might say x, we can't use f because that's used to the left, so we might say x is a function of y, and in this case g of y would be 4 minus 4/3 y. So the graph that we've created for our line x is a function of y and y is a function of x. This is an example of what we call a one-to-one function. And in the language of inverse functions, these two functions we found are inverse functions of one another. The domain of a function is the set of values for the independent variable, for which there is a corresponding value for the dependent variable. The key that we want to focus on is that we're looking for possible values of the independent variable. In other words, if I have a function of x, we want the set of x so that f of x is defined. In our first example, f of x is a rational function. It's computed by division. For f to have a value in its domain means that I can't have something undefined. In this example, division is the problem, and we need to avoid division by 0. So we avoid division by 0. So my domain of my function f, domain of f, is the set of all x such that the division is a good thing. So x plus 2 is not equal to 0. In order to find the domain, I need to find the solutions to this inequality. X plus 2 is not equal to 0 has a solution, x plus 2 not equal 0 has a solution x not equal to negative 2. And so if I think about this on a number line, here's the number negative 2, this point is not included and everything else is. And I write this in interval notation as all the points to the left of negative 2 union all of the points to the right of negative 2. And that would be the domain of my function. In my second example, I have g of x is the square root of x squared minus 3x, which means I'm going to be taking the square root of a number, and a square root has to have a positive value inside. So avoid taking the square root of a negative. We can take a square root of a positive or a 0, but we cannot take a square root of a negative number. So the domain of G is the set of all values x such that, well, what has to be true? The function or expression inside the square root, which in this case is x squared minus 3x, had better be greater than or equal to 0. We have to avoid the negatives. In order to find my domain, I need to solve the inequality. And so I solve the inequality by using factor sign analysis. X squared minus 3x greater than or equal to 0. I have my factors x times x minus 3 has to be either positive or 0. And again, I can think about my number line. For each factor, I identify where it's 0. So I have 0 and at 3. Those are my zeros. And then I test the signs. And in this example, if I'm to the right of both, they're positive. So I get positive times positive is positive. Between 0 and 3, like at 1, x will be positive, but x minus 3 will be negative. So I get a negative value in between. And if I pick a number to the left of 0, maybe negative 1, I get negative 1 times negative 4. That'll be positive. And so I have my sign analysis. I want positives or 0. And so when I find my solution set, I will include the interval to the left and right, including the edges. So my solution set is negative infinity to 0, including 0, union 3 to infinity, including 3. Finally, for my third function, k of x equals x cubed minus 3x squared, this time there's nothing that can go wrong. We can always cube a number, we can always square a number, we can always multiply by 3, and we can always subtract. So there's nothing to avoid. This is always defined. And so the domain of this function will be all real numbers. The domain of our new function k will be all real numbers. One way to do that is with the symbol r, or the interval from minus infinity to infinity. Finally, I want to say something about function notation. If I have a function defined by a formula f of x, then function notation, where you take the f, put in parentheses any expression, then whatever operations would have been done to x in your function are instead implied to the entire expression. So for our example, I have a function x squared minus 3x. What that means is I take x and I square it. So my operations for this function, I'll take x, I'll square the value. Then I'll take x again, and I'll multiply by 3. And then I'll take those two results, and I will subtract and find the difference. And so anytime I take a function, I'm going to do those operations. So let's take an example here. F of t plus 1, we'll take t plus 1, and we'll square it. And we'll take t plus 1, and we'll multiply it by 3. And we'll take those two values and we'll subtract. And this is how I calculate the value of my function. Let's do the same thing now. F of 2 plus h. We take 2 plus h and we square it. I take 2 plus h and I multiply by 3. And I find the difference between those two expressions. In our third example, what's the function value at x plus h? Well, I do the operations. I take x plus h and I square it. I take x plus h and I multiply by 3. And then I find the difference. This is how I calculate the value of my function. Now we often need to simplify it, but that's algebra, that's not function notation. So let's finish by simplifying. If I take t plus 1 and square it, I get t squared plus 2t plus 1. If I take 3 times t plus 1, I get 3t plus 3. So let's see, we have minus 3t plus 3. And notice how I used parentheses, because it's important that this minus sign I need to distribute into each term. So I get t squared plus 2t plus 1 minus 3t minus 3 for a final value of t squared minus t minus 2. In my second example, I'll do something similar. I square the 2 plus h. I get 4 plus 4h plus h squared. That's my 2 plus h quantity squared. And now I will subtract, distribute the 3, 6 plus 3h. And again, I need to distribute that negative sign to both terms. So I get 4 plus 4h plus h squared minus 6 minus 3h. Combining terms, I get negative 2 plus h squared. So there's my simplified formula. And let's finish by doing x plus h quantity squared minus 3x plus h. So I get x squared plus 2x times h plus h squared. That's the quantity x plus h squared. And I need to subtract 3x plus 3h. And when I distribute that minus sign, I get x squared plus 2xh plus h squared minus 3x minus 3h. And that's as simplified as I can go right now. And that's function notation.